Okay, so welcome. Good evening, everyone. It's a pleasure to have Sthitadhi Roy visiting us from ICTS. Sthitadhi got his undergrad degree from IIT Kanpur, where he got this integrated 5-year. He was part of the integrated 5-year MS program, MSc program at IIT Kanpur. After that, he moved to the Max Planck Institute for the Physics of Complex Systems in Dresden, where he worked with Roderick Meusner, and got a PhD from there, and then moved to Oxford, where he primarily worked with David Logan and John Chucker. And he moved to ICTS early last year, and he's been there ever since. So Sthitadhi is an expert in quantum systems, interacting quantum systems, which are far from equilibrium, and he's also an expert in many-body localized states and so on. So one thing I would like to tell you is that he's going to leave fairly soon after the talk, so if you'd like to chat with him or catch him.
Ajit, for the very kind introduction, and also thanks Shantanu for inviting me to give this talk. So I'll talk about dynamical phases of quantum matter in measurement hybrid dynamics. Now this might seem a bit of a jargon-filled title, but hopefully by the end of this, by the end of the talk, I would have explained what some of these things actually mean. So I should mention that because this is a colloquium talk, I've tried to keep it extremely general and sort of tried to strip it of all technical details, but I'm pretty sure that I have done it at the cost of some scientific accuracy, as well as almost certainly made it a bit boring for some of the experts in the audience. So yeah, as Ajit said, I mean, if you have any questions about the details or otherwise, absolutely do catch me after the talk. Okay, so what am I going to talk about? So should I wear it up? Yeah, so what I'll talk about is basically, here is the abstract that I wrote. Now let me just read it. So I basically say that unitary quantum dynamics in many body systems, in quantum many body systems, leads to information scrambling. And I'll explain what information scrambling means. And that is accompanied by an unbounded growth of entanglement entropies. So to put it very simply, this basically means that if you have some information in a state which is stored locally, then it gets scrambled across all the degrees of freedom in your quantum system, such that it becomes very, very difficult to retrieve it at a later time via some local probes. And this is sort of accompanied by, actually, is the pointer visible? Yeah. So, and this is accompanied by, or in some sense, seeded by the growth of entanglement in the system. Now, this is a fundamental obstruction to establishing quantum order or defining the notion of quantum phases in generic interacting quantum many-body systems. So, like a large fraction of quantum many-body physics or condensed matter theory, if I want to call it, deals with very new or interesting phases of quantum matter which are stabilized only at very low temperatures, or more specifically in the ground states of quantum Hamiltonians. But what we want to do is we want to have some sort of new notion of phases or quantum order at very highly excited eigenstates, right? So the fact that, and as soon as you try to access highly excited eigenstates, it basically means that you are accessing things at all energy scales, time to, if you sort of think of it as time going to the frequency domain, and as a result of that, you don't have order at high temperatures, or you don't have out of equilibrium order. So more recently, we have begun to think about how to stabilize these kinds of order. Many-body localization is one way of doing this. Here, in this talk, I won't talk about many-body localization. Here, what I'll talk about is how quantum measurements can be used to sort of arrest this growth of entanglement. And in fact, even before we talk about order, you can actually define two kinds of dynamical phases, one of which has a very large amount of entanglement, which we call, technically speaking, which we call volume law entanglement in the steady states of the dynamics. And it separates from another phase where entanglement is very low, which we call area law entanglement, in some steady state of the dynamics. Of course, the state changes, but the entanglement structure does not really change. And once we establish that, basically once we have, using quantum measurements, once we have brought the entanglement under control, we can then start asking questions about, fine, now we have low entangled states at all times. Can we actually induce some sort of quantum order in them? And of course, the whole point of doing this is to talk about some kinds of order which you don't have in equilibrium systems. Otherwise, what's really the point of doing all this, right? So we'll talk about a particular kind of order which we call time crystalline order, and for this particular talk, I'll talk about measurement-induced time crystalline order. So that's sort of the rough plan of the talk. And then let me start with basically thermalization and entanglement growth in quantum systems. That's the first part, and the motivation of this part is to show why it is difficult to have order out of equilibrium order in generic quantum systems. So in order to sort of explain this, let's actually go back to our basics. Think of the first statistical mechanics course that you did. And the whole point is that we generically understand that systems, classical or quantum, thermalize. For example, if I take this block of ice and I leave it at room temperature, it's going to go into sort of a water phase. And you don't really need to know a lot of physics to do this, right? I mean, all of us know that this happens. This is because we have a lot of faith, and for good reason. We have a lot of faith in thermodynamics. We know that thermodynamics actually works. And what's the point of thermodynamics? The point of thermodynamics is that it allows you to have a macroscopic description of a system which is composed of many, many microscopic particles with very complicated interactions between them. Thermodynamics allows you to not think about those complicated interactions and just think about macroscopic properties. And although we are first taught thermodynamics in a school or in our undergraduate program, really the bridge between a microscopic theory and a thermodynamic theory is brought about by statistical mechanics. So statistical mechanics is really the bridge between microscopics and macroscopics, which is thermodynamics. So what this allows us to do is it allows us to define three important tenets of statistical mechanics and thermodynamics. So one is thermalization, which basically means that systems equilibrate at long times to some thermal ensemble, or it may not be the thermal ensemble, it could be some other ensemble, or the kind of bath the system is in contact with. Then, using those states that the system gets to at equilibrium, you can define what we call phases of matter. So different phases of matter are distinguished from each other by very different macroscopic properties. And once we have phases of matter, we can talk about phase transitions, because these are really singular changes in these macroscopic properties across these phase transitions. And this kind of gives you a phase diagram where you have some macroscopic variables and on your axis, and you can define the phases. For example, this is the phase diagram of water. Okay. Now, an important concept that underpins all of this is the notion of ergodicity, right? The point that the long time average is basically the same as taking a thermodynamic average or taking an average with some thermodynamic ensemble is really what underpins all of this. But as soon as we talk about these things, keep in mind, or even when we're talking about these things in our basic statistical mechanics course or thermodynamics course, we never asked where did the temperature come from. We sort of take it as granted that yes, there is a system and it's in some, as soon as I said room temperature, right? So the room or the atmosphere in the room acts as a bath for the system that I am thinking about. So we always think of systems in contact with some sort of an environment, some sort of a bath which gives it a temperature. It might give it a chemical potential, it might give it some magnetic field, if you are working with magnetic systems and so on. So that is where your definition of ensemble comes from. In order to define a thermodynamic ensemble, you need these quantities, the temperature and so on and so forth. But you can ask the question that how does this kind of thermodynamics emerge from coherent quantum dynamics in isolated quantum systems? Now, what do I mean by isolated quantum systems? So, of course, no system, in our real world is perfectly isolated from anything else, but what the limit we want to think about is, imagine I have a system which has some inherent time scale, let's call that tau c, okay? And then we have some environment with which it's interacting, and the environment has some time scales which is tau e. So if the environment is extremely fast compared to, the environment is extremely slow compared to the actual system, then it's as if the environment didn't really affect the system. And that's the limit we want to be in. And in a way, in some sense, it is some sort of a theorist's playground. But the good thing is that there are now an increasing number of experiments which sort of achieve this limit. And some of the standard platforms for these are cold atoms in optical lattices, trapped ions, superconducting qubits. Superconducting qubits are extremely important nowadays because two of the leading quantum computing efforts in the world by Google and IBM are actually using these superconducting qubits to sort of develop and make their quantum computers. And we have nitrogen vacancy centers in diamonds. These are all sort of, each platform has its own pros and cons, but superconducting qubits is indeed one of the most promising of them, and so is cold atoms. And for example, here is an experiment from Emanuel Bloch's group in Max Planck, Germany, where what you can see is that he's tracking, forget about what this quantity is, he's tracking some quantity in time, and notice that this time is being measured in units of h bar over j. J is the intrinsic energy scale of the problem, some sort of a coupling constant. And notice that he has actually managed to get to 300. So basically you're looking at coherent quantum evolution up to at time scales which is 2 orders of magnitude larger than the inherent energy scale or inherent time scale of your problem. So this is fantastic because in traditional solid state systems you simply cannot do this. Traditional condensed matter systems like materials have so much where the equilibration times are so small that you'll never be able to actually look at the dynamics. You'll almost instantly see the equilibrium state. Okay? So that gives you a bit more motivation to actually look at these isolated quantum systems. So what these kinds of experiments actually do is they prepare some initial state, they do a coherent quantum evolution of the state using some Hamiltonian or using a set of unitary gates that you might design, and then you have some final state on which you eventually do some measurements. And in principle, you can do the measurement and use that state as an initial state for another cycle. So in principle, you can repeat this cycle over and over again. So all of this amounts to basically designing, manipulating, and measuring quantum states dynamically. So this is the kind of thing that these experimental platforms actually try to do. So then let's actually go back to the theoretical question we were asking, which is how does thermodynamics emerge from coherent quantum dynamics in isolated systems? So if we go back to our thermodynamics, we say that the probability of a particular state is given by e to the power minus beta times the energy of the state. Beta is the inverse temperature, right? This is what all our StatMech books tell me. So now that I have an isolated system, how do you even define its temperature? So the way you define the temperature is basically, in an isolated system, you may not have a notion of temperature, but you do have an energy spectrum, right? If I give you a Hamiltonian, it might be a very difficult task, but that's a different issue. Formally, in principle, you can calculate all the eigenvalues and eigenvectors of it if you had a large enough computer or enough number of qubits in a quantum computer. But in principle, you can do this. So you take a set of states which are very closely spaced in energy, which I have sort of denoted by the red block here, and you say that I'm looking at this particular energy E, and you solve a transcendental equation. You say that if this has to admit a temperature or a thermodynamic description, then this energy E should be equal to the trace of H being the energy operator, it's the Hamiltonian operator, with respect to some thermal ensemble, which is e to the power minus beta H. So this gives you a transcendental equation which you can solve to get beta out. The upshot of this, that to any sort of set of states at an average energy E, you can uniquely ascribe a temperature via the expectation value of the Hamiltonian operator. Okay? And in this sense, a single eigenstate is a natural analog of a microcanonical state. So this is a very different kind of statistical mechanics it seems we are talking about, but at the end of the day, it's not that different because you eventually, this is just fixing the temperature. Once I fix the temperature, the statistical mechanics looks identical to what you did for equilibrium StatMech. Okay? So this solves the first question, that fine, given an isolated quantum system and given its eigenstates, I can ascribe a temperature to this. The next question you can ask is, how is thermalization compatible with unitary quantum dynamics? So we know that generic quantum dynamics for isolated systems is unitary. E to the power minus I ht is a unitary operator. So the point about this is, suppose I start with some initial state which is pure. Okay? Now I evolve it with a quantum Hamiltonian for some time, and my expectation is that it should equilibrate and I should get a thermal density matrix at the very end, which should be proportional to e to the power minus beta H, right? But obviously this cannot happen because unitary dynamics cannot change the purity of the state. So a pure state under unitary dynamics always stays pure. So there is no way this can go to a mixed state. There's no way it can go to a thermal state. And you are forced to, even if you don't like it, you are forced to draw the conclusion that the entire system cannot thermalize. Okay? Now, actually what happens is, this is true, but what happens is thermalization happens locally in isolated quantum systems. So the way you can understand this is, suppose you take an isolated quantum system, which is this blue blob that I have drawn here, and you look at a small subsystem of this, which I call S. It's the orange bit, and everything else is S bar. So what you can say is that you take this density matrix and you trace out S bar, okay? And you look only on the reduced density matrix of S. This is equivalent to saying that I'm only interested in observables which are local and have a support only on S, okay? So once you do that, you do indeed find that these local observables actually have an expectation value which is very well given by the thermal expectation value with this temperature beta set in the way I discussed above here, okay? So that gives you this idea that thermalization actually happens locally. And for local observables, you do get a thermal expectation value. And the essential point is that the rest of the system acts as a bath for the subsystem. Now, of course, there is nothing special about that orange blob I drew. You could have taken any small subsystem. So if you take any small subsystem, the rest of the system acts as a bath for that particular subsystem, and it eventually thermalizes under the action of that bath. And the temperature is basically set by the state that you started with. Okay, so once we understand this, let's dig a bit deeper and try to put it slightly on formal grounds. So the main formal concept underlying all of this is what we call the eigenstate thermalization hypothesis. Now, some people would argue that at this stage it's no longer an hypothesis, and there are some quasi-proofs of this, but the name has stuck and it's called the eigenstate thermalization hypothesis. So it's basically the same idea that I said before, that a single eigenstate at a particular energy E is representative of a microcanonical ensemble at that particular energy, okay? So that tells you that each eigenstate is thermal, is like a thermal ensemble, although it's not really an ensemble. It's like an ensemble. And what that means is that if I take an eigenstate at energy E and I calculate some local observable in that, it should basically give me the expectation value of that same observable computed in a thermal ensemble at temperature or inverse temperature beta set by this energy E. So that basically it says that each single eigenstate is a thermal state. Now, what you can do a numerical experiment and you can try to compute this. You can try to compute the expectation value of some local operator and try to plot it as a function of the energy eigenvalue. And what you actually see, and this is the hallmark of a system which satisfies ETH, or eigenstate thermalization hypothesis, is that it's actually a smooth function. So, of course, there is some scatter here because this is some result for a toy finite size problem. But the point is, if you could simulate an infinitely large system, this would actually be a completely smooth curve. And this is not unexpected, right? Because the energy is changing continuously, so the associated temperature is changing continuously. So this expectation value better change continuously, okay? Now, things or systems which are not ergodic, which do not satisfy the eigenstate thermalization hypothesis, actually don't satisfy this. And there you can see rapid fluctuations in this expectation value as a function of energy. But yeah, as I said, we'll not talk about that for now. So the point here is that, as I said, the rest of the system acts as a bath. So that means that there has to be, either in this eigenstate or as time evolves, there has to be very complicated non-local correlations building up in the system, right? So one way of understanding this is, suppose you take this system and you develop or you sort of divide it into many small patches. Each small patch here is a different color. And you ask that how is it that the rest of the system acts as a bath? So for the rest of the system to act as a bath, it has to have very efficient information or quantum information exchange between all of these subsystems. And because no subsystem is special, basically there is a web of these complicated non-local correlations. And this is probably one of the simplest ways of visualizing quantum entanglement, that you have many degrees of freedom in your quantum system. The information of the total state is not just the information of each component put together. It really is a bit more than that, because the information of a particular patch is not there only in that patch, but it's shared with every other part of the system, and the same for any other patch. And that's what we physically mean, or that's what we say, mean when we say quantum entanglement. Now, the point is that as an isolated quantum system thermalizes, different parts of it get entangled with each other, because as the system evolves, the different parts get entangled, and the information that was initially there in a patch begins to get spread out across the whole system. This is exactly what we mean by information scrambling, that you cannot simply measure that local part and get all the information out. You really have to look at the whole system. And this is also often called information scrambling, because the information that was there initially locally is now hidden in some very non-local correlations, which basically is happening because the different parts of the system are getting entangled with each other. So the crucial point is the growth of entanglement not only goes hand in hand with thermalization, it's almost a necessity for thermalization to happen. All right? So that's where quantum entanglement enters the picture. Now, let's sort of take a step back and sort of slowly summarize what we said so far. So we said that in isolated quantum systems, thermalization happens locally. The rest of the system acts as a bath for a local subsystem, and the temperature is set by the initial state of the system. And thermalization goes hand in hand with entanglement growth. Now, the crucial point here that I have highlighted in red here is, or maroon, is that the temperature is set by the initial state of the system. Now, or of course, it's not a complete statement. The temperature is set by the initial state of the system and its energy measured with respect to the Hamiltonian that you are dealing with. Okay, so that actually raises a question that how do you even define a temperature when you may or may not have a well-defined spectrum? So when can that happen? That can happen when you have, for example, a time-dependent Hamiltonian. Okay. Because if I have a time-dependent Hamiltonian, then the spectrum is actually changing at all times. Suppose my Hamiltonian has some noise, or you have given me a quantum computer and you want me to do a specific task, and you have told me what the algorithm is. So I'm doing all the steps one by one, and at each step at each time step, my actual process is changing. So I don't actually have a Hamiltonian dynamics. I mean, this is often what as physicists, we often call this quantum circuit dynamics. Basically, the idea is that you have a set of qubits, which could be spins, or just think of them as some quantum degrees of freedom, and you have a set of gates, which can either act on 1 qubit, it can act on 2 qubits, it can act on 3 qubits, and so on. And these really are unitary operations on the state. So we call them gates because we are borrowing literature from the computer science community, but really these are a set of unitary operations that happen between these different qubits. Okay, so what all of these devices, for example, Google's device or all the superconducting devices do is that they apply a set of unitary gates sequentially, and these unitary gates might or might not repeat after some cycle. So basically, the dynamics becomes a discrete time periodic dynamics. There can be some extra noise on top of it, but even without noise, this is some discrete time periodic dynamics, let's say. That's the simplest case. Of course, the dynamics need not be time periodic, but time periodic is the simplest case. So this is good because for the last 8 years or so, time periodic systems have been studied a lot. So we know a fair amount about the emergent statistical mechanics of periodically driven quantum systems. So what we know is the following. So there are 2 papers that I'd like to flash out. I mean, there are many more papers on this, but these are among the earliest 2 papers. So what they are doing in these papers is they have a generic ergodic non-integrable quantum many-body system, and they have applied some periodic drive to the system, and they're asking that at late times, what is the nature of the state? So what they find is that if you look at here, they say that essentially this happens because the flow k eigenstates. So flow k eigenstates are the eigenstates of your time periodic unitary. So just as if you had a Hamiltonian, you could have worked with the eigenstates of h, or you could have worked with the eigenstates of e to the power minus iht, for example. Here, what you do is you work with the eigenstates of the operator that generates your time evolution. So they say that it becomes a mixture of exponentially many eigenstates of the undriven Hamiltonian, which are thus drawn from the entire extensive undriven spectrum. So to unpack, what this essentially means is that the state, if you look at its decomposition over the eigenstates of the entire Hamiltonian, it's more or less democratic, right? It has weight over the entire spectrum of some undriven Hamiltonian. That means that there is the state is not really choosing any energy with any preference. What it really is doing is it's sort of going and democratically populating the entire spectrum. So that means that e to the power minus beta e does not really depend on e. And that means that beta is very close to 0. And beta is the inverse temperature. So beta 0 means that the temperature has gone to infinity. And this is what we call infinite temperature states. Like the system has absorbed as much energy as it could, it has heated up as much as it could, and it cannot take in any more energy. And that's what we call infinite temperature states. And a very concurrent paper basically says the same thing exactly in this language, says that the effective Hamiltonian, if you want, looks like a non-local Hamiltonian with multi-spin interaction terms, and the driving leads to the equivalent of an infinite temperature state at long times. So this is basically not a very good news, because what this means is that my temperature has gone to 0, beta has gone to 0. So at infinite times, my operator is simply the trace of whatever operator I was looking at. And that's extremely bad news, because the trace of an operator, or most operators that we are interested in, is trivial. So that means that the system not only has lost all memory of its initial state, not only has it failed to retain any quantum information, it basically has given me the most featureless, the most boring state you can actually think of. And this is basically an obstruction to having any kind of dynamical quantum order. It means that even if you start with some ordered state and start, have some sort of quantum circuit. So by the way, this is called a quantum circuit because there's a set of unitary gates and this looks like a circuit. That's it. So the point is that even if you started with an ordered state and had some quantum circuit acting on it, once you run the circuit for long enough, the system will actually heat up to infinite temperature and become completely featureless. And that means that you cannot have any order dynamically speaking. So then you can go back and ask that, okay, what can we do so that this order is retained up to some, to some degree. So in fact, in this picture, there is a slight hint to how you might actually do this. And that is basically this layer of measurements, okay? Because as we discussed that what we need to do to stop this heating up or stop this thermalization is to stop the entanglement from growing. And we know where, and as I'll show, and I think many of you already know, doing quantum measurements actually helps reduce the entanglement. So it's possible that measurement can arrest entanglement, and once you actually have a lowly entangled state, you can ask that can you actually stabilize a new phase of matter, okay? So that takes me to the next part of the talk, which is interplay of quantum measurements with thermalization and what we call entanglement transitions. So let me first sort of go back to this picture very briefly, that you have some initial state, you have a coherent quantum evolution, you have a final state, and then you have measurements. So let's look at this in the simplest setting of there being two quantum spin halves or two qubits, okay? Suppose you started with some state, I don't care what that state was, you did some evolution, and you went to possibly one of the most entangled states you can write with two qubits, okay? This is a well state. Now what you do is you try to measure sigma z on the first spin, okay? You do a projective measurement of sigma z on the first spin. Now we all know from our basic quantum mechanics that once you do a measurement, what you do is you project the state of that system onto an eigenstate of the operator that you are measuring. And the probability with which you project it onto some state is basically given by the expectation value of, or is related to the expectation value of that operator. So in this case, it's an equal weight superposition. So with equal probability, the state either collapses to up or down, or it goes to down up. But notice that as soon as you did the projective measurement, the state actually went from being a maximally entangled state to a completely unentangled state. And the entanglement of the two spins got completely destroyed. Now, of course, this is sort of a fine-tuned example I chose to make the point, because this is just two spins, and I chose a particular measurement which basically made it a product state without any entanglement. But of course, you can do this more generically. So suppose I have some state, and I'm representing the state as some legs, which the legs are the qubits that are associated to this. And then let's say that before I measure, and I want to measure this particular site, which I sort of call I. So before I measure, let's say that the state was given by some state phi, which is a state on all the degrees of freedom except I, which is phi up. So it's C up times up on I cross phi on phi up, plus C down times down on I cross phi down. So this is the most generic, or this is some or let me put it this way, any state that you give me, I can write it in this fashion. Okay? So now, once I do a measurement, what ends up happening is that with probability C up mod square, I'll project it to up I cross phi up. With probability C down square, I'll project it to down I cross phi down. Now, just by looking at the structure of this state, you can already see that the spin at site I actually gets disentangled from the rest of the system, because I can write it as a product state. So that essentially means that this spin I has no information about the rest of the system. The rest of the system has no information about the state of the spin at I. Okay? So it's clear that the entanglement entanglement between two parts of a system, the contribution of site I from that entanglement has gone away, right? So that means that measurements do indeed help in reducing entanglement. Now, this just tells you that entanglement is reduced. It doesn't really say that there is a qualitative difference in the entanglement structure. So let me try to motivate that using a StatMech mapping of a certain problem. So one of the ways in which we like to study entanglement or entanglement growth is via something which we call an entanglement cut in space-time. So let me explain what that is. So imagine I have a set of qubits and I do a set of operations on those qubits, which are these blue circles or blue rectangles. Okay, these are some, let's say these are some unitary operations. Each unitary operation here can be different, and as you can see, they have randomly been placed between some qubit and its neighbor. Now, I want to know that if I started with some state here, let's say it was a product state. Once I basically evolve it for some time t, then what is the entanglement between two parts of the system? So suppose I make a cut here and I say that this is subsystem A and the 3 qubits to the right are subsystem B, and I want to know what is the entanglement between A and B. This is a very, very hard problem. You cannot really compute it exactly for generic interacting integrable systems, non-integrable systems. What you can do though is put a bound on it, and that's going to be very useful. So basically what you want to do is you want to actually take this circuit, think of it as some space-time picture. So space runs horizontally, time runs vertically, and say that I am going to basically draw a red line which cuts through some of these black lines and separates the subsystem A from subsystem B. Okay? Now any such cut actually incurs some cost, and if you think of it that way, the entanglement is basically bounded from above by the number of these black legs that the red line has to cut. Okay? Now the simplest way of thinking about this is, suppose you actually compute the reduced density matrix, then the rank of the reduced density matrix is necessarily equal to the number of cuts you made, right? Because every time you make a cut, you lose some information about, or every time the red line crosses a black line, you lose some information about A lose some information about A into B, and that basically gives you an extra eigenvalue in your reduced density matrix. So this is sort of the heuristic way of explaining this, but of course you can show all of this mathematically very rigorously, that indeed that the rank of the reduced density matrix is at most q to the power s cut. Q is the local Hilbert space dimension. So if you are dealing with spin half, think of q is equal to 2. Now the point is that of course this is an upper bound, right? So you want to minimize s cut. That's going to give you the best bound. So the best bound is nothing but given a circuit, given the geometry of the circuit, you basically want a cut which passes through the smallest number of such legs. Okay? What you're not allowed to do is you're not allowed to cut through a unitary. You're not allowed to cut through a blue box. And of course this then becomes a statistical mechanics problem, and you can solve it. Lots of very interesting features emerge. You can explain the linear growth of entanglement entropy using this picture. You can explain how the fluctuations in the entanglement entropy scale with time and so on and so forth. It has interesting mappings to statistical mechanics problems of directed polymers in random media, on surface growth problems, and related to the kind of things that people see in the context of KPZ equations and so on. I'm not going to go into the details, But the point is that such a picture is very useful as far as understanding the basic picture of entanglement growth in unitary dynamics is considered. Now you ask the question that what happens when I start putting in measurements? Okay, so what I'm doing here is that I have the same circuit as before, but as time goes, with some probability, I randomly start doing projective measurements on some of the spins. And each measurement here is basically shown by this yellow box. So this yellow box basically means that with some probability, I project the spin here to up and then normalize the state. So it's the same picture again that before I measured, the state was some generic state. After I measure, it basically becomes a spin state on the site I measured, direct product with the state of the rest of the system. So clearly, just after I measure, that particular spin is not entangled with the rest of the system. So if my cut, this red line, goes through that, then I am not paying any cost for it, right? So that tells me that if I have measurements, then there is no cost of cutting a leg which has a measurement operator on it. So this is basically showing that measurements actually help you decrease entanglement, but in a many-body setting. The statistical mechanical mapping to this is basically say that wherever I had a measurement, it's as good as not having the link there. It's as good as having a broken link there. And now you can ask the question that is there a cut that I can find which is optimized that it goes through the maximum number of already broken lines. Okay? Now that is basically, for example, here we have a cut which basically in this case obviously I've drawn it like this, but generically there's a possibility that you might be able to find a cut which does this. Now notice that I do not actually have to pay any cost for this cut. So the entanglement in this case is obviously going to be 0. Now if you think of this as some graph, as a classical graph, think of these blue rectangles and these black lines as nodes and links of a graph, then this basically looks like a percolation problem. The question is that if I start off from the left end of the system, I start off in the deep subsystem A part of the system, and then I try to grow a cluster by following whatever links I have available to me, will I be able to have an infinite cluster that goes all the way to the extreme end of subsystem B? And the answer in this case is no, right? Because you actually have separated the left half of the system from the right half of the system by doing measurements. So that's of course an extreme case. What you can have, as we know in percolation phase transitions, is that you can have a phase where that basically you do not have there is a finite probability. The probability may not be 1, but there's a finite probability that you have an infinite cluster, and there is a phase where the probability is 0 of having an infinite cluster. So this basically looks very much like that same transition, and this tells me that there must exist two phases in the system. One which has a lot of entanglement, which we call volume law, one which has basically 0 entanglement. Of course, I'm not yet talking about area law, but what really happens is that the classical picture does not exactly work this way, because this cut can actually fluctuate, quantum mechanically speaking. So what you end up having is basically sort of two phase transitions. One is a classical percolation phase transition. This is where the circuit classically disconnects between the subsystems, and this is basically determined by circuit geometry. So obviously the entanglement here is 0. There is a phase, this is the measurement rate by the way, a low measurement rate, where basically just have very few measurements. So the cluster can grow as freely as it wants, entanglement can grow more or less as much as it wants. So in that case you have an extensive or volume law entangled phase, and in between you have an interesting phase where basically the circuit is classically connected by a few order 1 links, but that's not actually enough to give you volume law entanglement. You have order 1 entanglement in an extensively large system, so that's what we are going to call area law entangled. Okay? So there are deeper reasons for calling this area law entanglement, but for this kind of 1D systems that I was talking about, let's think of them as just there being order 1 number of finite cuts. When I say finite cuts, I mean the number of black legs that the red line had to cut through. Okay, so let's take stock. We have thermalization and entanglement growth as obstruction to dynamical quantum order, but what we have also shown is that if I have measurements interspersing my unitary dynamics, I can bring the entanglement under control. So the question now is, how do I actually exploit these hybrid dynamics to stabilize new kinds of dynamical order and phases which might have low entanglement? I'm going to talk about a measurement-induced time crystalline order. The first question you can ask is, what is a time crystal? Okay? In order to answer that, let me first go to a space crystal. And the simplest space crystal is something that we see and use and eat every day in our lives, which is basically sodium chloride, which is salt. And if you actually look at a salt crystal under a microscope, if your microscope is good enough, you'll basically see a cubic lattice. Now, why is this called, or what does this tell me about a crystal? A crystal basically is a regular periodic arrangement of points in space. So I have continuous space. From there, I pick a regular periodic arrangement, and that gives me a crystal. And from there, you can think about all different kinds of complicated crystals that you might have learned about. So on a slightly formal footing, what this basically means is that you have broken or reduced the spatial translation symmetry. So your sort of free space has continuous spatial translation symmetry, but now you have reduced it by saying that you encounter a point only if you move move in integer steps of the lattice spacing. So this is a reduced translation symmetry. You don't have enough freedom as you had before in terms of there being a continuous symmetry. So this is what defines a space crystal, that you reduce or break the continuous translation symmetry, or reduce or break the spatial translation symmetry of your free space. Exactly in the same vein, you can talk about a time crystal, that it's some regular periodic pattern of order in time, and which has to break or reduce time translation symmetry. Okay? So a very schematic picture is, suppose I have some system, and each color here represents a different kind of order. And I have some unitary operations. Let's say I have two unitary operations, u1 and u2, and I apply them sequentially. So now imagine it so happens that I'll give a more concrete example in a minute, but imagine it so happens that the first time I apply u1, blue goes to green, and then I apply u2, it goes to red, and then I have to do this, I have to repeat the entire cycle once more to get this blue order back again. Okay? So what actually happened here was that the unitary operations repeated after 2 time steps, but the order actually repeats after 4 time steps. So your original time translation symmetry was there in sort of 2 units per time, but your order actually has time translation symmetry of 4 it repeats after 4 time steps. So you again have reduced your time translation symmetry by half. Now this is still not a time crystal, because we want to think of time crystal as a genuine phase of matter. Because as a classic example, you can say that what about a quartz crystal oscillator which is sitting in all of our watches? It's not a time crystal, because a quartz crystal is not a stable phase of matter. The frequency at which most oscillators in our watches oscillates, which is 2 to the power 15 hertz, is very, very sensitive to how the quartz crystal is cut. If you take a different cut, if you change something in the crystal, the frequency actually changes. But that's not a phase of matter, right? A phase of matter has some stability in some phase space. It has to be a region in phase space. It cannot be a point in phase space. So for it to be a genuine phase of matter, we want this kind of a response to be robust to changes in parameters. Okay, and I'll explain what I mean by that. But let's go ahead with this idea that we have some periodic unitary operation that we are doing. It might not be a perfect unitary, right? So this is also something we demand, that as soon as we break the perfect periodicity of our protocol, the time crystalline order should not go away. Otherwise, again, it becomes very fine-tuned. So we need to have a setting where we have some periodic protocol with some noise, with some imperfections, but nevertheless, the system has a way of correcting those and eventually gives you some time-dependent order which has a reduced time translation symmetry. That's what our definition of a time crystal is going to be. Now, here is a very schematic picture of what a time crystal might look like. So suppose I give you a system, and let's say that it has 2, you can sort of divide its Hilbert space, or it can divide the space of states that the system can take into two towers. One I call the blue tower, and the other one is this orange tower. And the two of them, in their lowest energies, so the lowest energy states of each sector has a very different kind of order. So for example, a classic example would be that this is a ferromagnetic state with all spins up. This is a ferromagnetic state with all spins down. And this tower consists of states which have on an average positive magnetization. This consists of states which on an average has negative magnetization. Okay? So once I do this, then what I can do is I can define a protocol where I do an imperfect rotation. So I rotate my spins, but they're imperfect. As a result, I don't go from my ferromagnetic state to the sort of ferromagnetic state with all spins up to the ferromagnetic state with all spins down. I roughly go into some mixture of states in the negative magnetization sector. But then I actually cool the system down. And by cooling it down, I bring it to the perfectly ferromagnetic state with all spins down. So now I can keep doing this many, many times. So you see that again, my protocol repeats after 2 steps, but my order actually repeats after 4 steps. So this is how we can hope to build a robust time crystal. So what we want to do is we want to have these imperfections in the rotation corrected by measurement-induced cooling. So we want to have a measurement protocol which corrects for the state not being a perfectly ferromagnetic state at the end of each rotation cycle. So let me sort of say this in a bit more detail. So suppose I have a 2D quantumizing model on a square lattice. Okay, so I have a square lattice and I have square lattice and I have quantumizing spins. So I have a set of unitary operations. So the unitary operations are done in basically 2 time steps. So in the first step, there is some rotation of the spin about the z-axis, and then in the next step, there is some interaction between the spins. So x and z's are basically poly x and poly z operators. Now, obviously, what you see is that if j is equal to 0, which means that they are not interacting, and this angle is exactly pi by 2, then this is a trivial time crystal in the sense that this is a fine-tuned time crystal. So you start from the ferromagnetic state, you rotate all the spins by pi by 2, they basically go to the all down state, then you again go up and then you keep going down. So, but the point is that as soon as you have interactions and imperfections in this theta j, it melts the time crystalline order. Remember that those papers actually taught us that this kind of a periodic protocol generically heats the system to infinite temperatures, right? So as soon as I have some finite j or I have some imperfections in theta j, I cannot have a time crystalline order. So what I want is, we want to have measurements which stops the entanglement growth and heating up to infinite temperature. So this is easy to arrange for, because I just argued a while ago that using a sufficient density of measurements, you can drive the system into a new phase where entanglement is under control. What we now need to do is we need to restore ferromagnetic order at each step. And what does restoring ferromagnetic order mean? It basically means that you kill the domain walls that are caused by this imperfection. So a domain wall is basically a boundary between a region which has spin up and spin down. So you want to kill the domain wall so that there is no such boundary, which means that the state is perfectly ordered. So the way we do this is inspired by a classical cellular automaton that goes by the name of Toom's northeast center cellular automaton. It was developed by a Russian mathematician called Andrei Toom. So the idea is the following. So let's digress with a classical system for a while. Let's suppose I have a square lattice, but I'm showing only a triad of 3 spins. So these are classicalizing spins now. So what I do is I take a spin, which is the center spin. I look at its spin to the north, and I look at its spin to the east. And if I see that if both of them are anti-aligned with the central spin, I flip it. Okay? It's the same thing I do here. But you see what this does is, there was a domain wall like this, right here. The red is a domain wall. It basically kills the domain wall. Okay? So I hope this works. So you can actually simulate this on an actual square lattice. And here what is actually happening is that each line is a domain wall, and if you simulate this, you see that the domain walls basically shrink in a southwesterly direction. That's because, notice that this domain wall was like this, and it came down in a southwesterly direction. So that's what is happening collectively speaking, and you basically have order at some after running this cellular automaton for a while. So now what we want to do is we want to write down a quantum mechanical version of this, because this tells us, using measurements, because this tells us that this is one way of actually stabilizing a ferromagnetic order. So in order to do that, what we do is we define, so I think this and the next slide is the only two slightly technical slides I have, so let's go through that. So what I do is I define a domain wall operator between a spin at side j and j plus a. A can be the north spin, or it can be the east spin, okay? Then what I do is I do a projective measurement of this domain wall operator. So I do a projective measurement of a 2-spin operator, and obviously what it does is it either projects the state onto, because the eigenstates of these operators are either perfectly aligned states in X or perfectly anti-aligned states in X, or linear combinations of them. So basically, the eigenstates of this are either states with no domain walls or states with domain walls, which is sort of a trivial statement. So the point is that once I do a measurement, the state gets projected onto an aligned configuration, in which case this is 1, and there's a probability of that happening, which is given by the expectation value of this operator on the state that I am in. This is a state which corresponds to no domain wall, or it can anti-align it with some probability which is given by this, and this corresponds to the presence of a domain wall. So already you see that this is clearly not going to be as effective as the classical automaton, right? Because here there is this stochasticity coming from the inherent nature of quantum measurements, that you are trying to project it somewhere, but to which state it gets projected is not something you can determine beforehand. Okay, so the point is, then what you do is you put a conditional unitary on this. What that means is that if both the neighbors are anti-aligned, then you correct the error by rotating the spin using a unitary operator. So that's basically this particular step. So you can put all of this together and try to write this as a quantum channel. So let me explain what is going on in this. So you had a state of the system which we call rho. What you did was you put a projection operator on the east neighbor. So WE is either plus or minus 1. So basically you either projected the east spin onto a domain wall state or to a no domain wall state. So either an aligned state or an anti-aligned state. And you did the same thing for, you projected the two neighbors onto aligned domain wall configurations or anti-aligned domain wall configurations. And then depending on what this WN and WE are, you either put the unitary gate like this here, or you did not put the unitary gate. Okay, and these pi's are the projection operators. So all that basically means is, and then you of course sum over all the possibilities of WN and WE, which are plus and minus 1. So the point is that the probability with which it gets projected onto something basically depends on the state that you had. Okay, so this is how you write down this measurement unitary hybrid dynamics. Right now we only have the measurement in terms of a quantum channel. So this is the protocol we are trying to follow. So what we actually do is we don't evolve a density matrix, we evolve a quantum state and then average over various things. So let me quickly run through this. So what we do is we take a state at psi t. The state at the next time step is basically given by two unitaries. One is this spin rotation and the other is this spin-spin interaction. Now notice that these coupling constants actually, or particularly this field, actually depends on time as well. So that's where not only it is imperfect in space and it's not close to pi by, or it may not be equal to pi by 2, it also fluctuates in time. So obviously without measurements the system is going to heat up to infinite temperatures. But then what we do is we do a measurement induced Toombs northeast center rule, which is what we say is that we put a probability of measuring, which we call P NEC. So with probability P NEC times the probability of projecting the east and north at a given site to some domain wall configuration, we do that projection, and depending on the projection we apply the corrective unitary. If not, with some probability 1 minus P NEC, we don't do anything. So we are saying that this protocol is so robust that you don't actually have to correct for it at every step. Okay, you can actually correct for it once in a while also. That's enough to actually stabilize the time crystalline order. So here is some evidence, numerical evidence for that. So what we are doing here is we have to, let's say we have, there are many parameters in this problem, but let's fix all the parameters and look at a two-dimensional phase diagram. So on the x-axis, I have this the mean value of the field that I am applying to rotate the spins. So obviously at pi by 2 it's the best, and at 0 it doesn't rotate at all. And on the y-axis I have the probability of measuring. Okay. So what you see is that when you are at some very large value of, or when you are at a value of h which is very close to pi by 2, so h is 0.9 times pi by 2, and you also have a very high error correction rate, you actually simulate a time crystal. So this is the magnetization as a function of time. So you see two branches, because at even times the magnetization is 1, at odd times the magnetization is -1. So it's really oscillating, and you see that as you increase the system size in your simulation, it actually gets better and better. And basically already on a 5x4 system, it has basically it's almost looks like it does not decay. On the other hand, you can melt the time crystalline order in two ways. One is that you stick to a very good value of h, a favorable value of h, but you reduce the error correction rate. So you make PNEC like 0.1 somewhere here, and you see here that the time crystalline order very quickly decays and the magnetization goes to 0. The other thing you can do is you can keep the the error correction rate very high, but you can keep, or you can move this h to some value which is somewhere here. So in this region in the middle, and there you again see that the time crystalline order basically dies off very quickly. So you sort of do this over a parameter, you do a parameter scan of this, and this is the phase diagram that you end up with. So basically the point is that the closer you are to h equal to pi by 2, the less error correction you actually need via the measurements to stabilize the time crystal phase. Now, and this is the paramagnet phase, because this is the phase where all the spins literally get jumbled up. And also, not only can you stabilize this time crystal order, which is not possible in an equilibrium system, as a byproduct you also get a measurement stabilized driven ferromagnet, because this is a ferromagnet because basically you are not really rotating the spins. So you started with an all up state, you slightly rotated the spins, but then the measurements came along and they again put the spin back to wherever it was. So that's why you have a ferromagnetic phase, and in some sense these two phases are, I mean, I don't want to say dual to each other, but very like each other, except one has an additional rotation between the cycles. Okay. So I think that's all I wanted to say. This is something which we call an absolutely stable spatiotemporal order of the time crystalline kind. The term is called absolutely stable because this order does not really depend on any symmetries or anything specific to the system. You can add whatever kind of imperfections or noise you want to add to this protocol. You can change the measurement rate, you can put noise in the couplings, you can put disorder in the couplings. The time crystalline order survives. So that's why we call it an absolutely stable spatiotemporal order. Okay, so I'll just say one more thing, which is how do you actually do this 2-qubit, how do you implement this 2-qubit measurements on some of the available quantum computing platforms. So what you do is, so suppose this red circles here are basically my square lattice. For like in the centers of the squares, you put ancillary qubits, which help you do the measurement. So the way you do that is, suppose I want to measure this the north, like I want to measure the north domain wall operator between these two spins. So I find out the ancillary which couples these two, and whatever, so let's say this is J and this is J prime. So whatever the state was, I prepared my ancillary qubit in a state which is polarized in the positive x direction. So that's this plus state. And then I apply two C0 gates on this. So this is not exactly the C0 gate, but this modulo some single site rotations. These are two C0 gates. Now the nice thing is that once you write this in terms of the C0 gates, what you can do is you do a bit of algebra, and what you find is that you can actually you can decompose this into something which is only plus on the ancillary qubit and something which is minus on the ancillary qubit. Okay, notice that the operators here have nothing to do with the ancillary qubit, which I'm denoting by B. And this pi plus and pi minus are basically projectors onto the no domain wall subspace and the domain wall subspace. So then once I apply these C0 gates, what I do is I do a projective measurement of this ancillary qubit along the x direction. So then I either pick up this or I pick up this. And one of them corresponds to the domain wall states, the other one corresponds to the no domain wall states. And that's how you basically implement these domain wall measurements, and you can sort of you can propose this to an experimentalist who can possibly do this. Okay, so I think let me quickly summarize. So I started off by showing that how thermalization and information scrambling in quantum system goes hand in hand with entanglement growth. Then I showed that you can basically stop this entanglement growth by having enough number of measurements, which basically gives you a measurement-induced entanglement phase transition. And finally, I showed that once you have got the entanglement under control, you can actually use the measurements as an active feedback to stabilize a measurement-induced time crystalline order. So let me just highlight the two papers in the course of which I basically learned many of the two things, and if you're interested in more details, these are the two papers to find these things about. And yeah, so let me end with the summary slide. And yeah, thank you for your attention.
Questions?
Okay, thank you for the nice talk. So I have that question when you said when you have some external periodic drive, and so irrespective of that time that we are seeing the so the state spreads over whole the so that is the eigen, it spreads over eigenstate of which system, at original edge or?
Basically what you can do is, suppose you have some time periodic Hamiltonian. So okay, if you have a time periodic Hamiltonian, you can think of it as, let's say the time period is t, so you can average the Hamiltonian, and you have a part of the Hamiltonian which does not depend on time, and then you have a part which depends explicitly on time in a periodic fashion, right? So then you can say that you basically took a Hamiltonian which was described by the static Hamiltonian, and then you put the external drive on top, and then you can ask that what happens to the states in the eigenbasis of this external time independent averaged out Hamiltonian. Yeah, but it doesn't really matter. That's the whole point. If it heats up to infinite temperature, then no matter what basis you take, it's going to the density matrix is going to be identity, right? So that's why you don't have to think about which basis you see or which basis you choose, because an infinite temperature state is an infinite temperature state. It doesn't care about the basis.
Yeah, the second question I have regarding that graph to induce put a bound on the entanglement growth. So so this is as that
Okay.
So every time we are measuring, we are dividing the system into different subsystems, different sides.
Yes. No, I'm not dividing it into different subsystems every time. So I have a system, and I have said this is my subsystem A and this is my subsystem B. Now I want a cut which separates all the legs to the left and all the legs to the right. But of course the cut is allowed to fluctuate in the bulk of the circuit.
Okay.
Right? But all I want to do is that, the point is that the entanglement I want to compute at this particular time, right? Starting from an initial state. So I want this should have basically come here, but what I want is something that starts here and closes.
Yes, yeah.
Of course, it's allowed to fluctuate in between. Okay? And the point is that the best bound is given by when I have the minimum number of such cuts.
Yes. Suppose at the last point we did exactly the measurement at where the cuts, so then we'll get the entanglement to be 0.
No, sorry, can you say that again?
So if you do the towards the last, towards the end.
So you want to put a measurement somewhere here?
Yeah.
No, that's not going to make it 0, right? Because you'll also have to cut the other, because that will basically reduce only one bit of entanglement. Because there are also, in order to make this 0, you have to do this fine-tuned thing that I did, was we have to measure everything, all of them.
All cuts.
All the cuts. You have to completely disconnect.
Thank you for the talk. My question is that you said that if we have time periodic Hamiltonian, then the long time state will be infinite temperature, right? So my question
for a generic, of course there can be fine-tuned situations like free fermions and integrable systems where it may or may not happen.
So my question is, physically, why is that undesirable? Because if you have,
because if it's undesirable, because then whatever operator you calculate, you'll basically just get the trace, right?
You'll get trivial.
Just get the trivial.
So maybe to get a non-trivial answer, we should be having not time periodic.
But
Right.
something, I mean, that will make it even worse. So if you have something which is not time periodic, so you see, what actually okay, one way of understanding this periodic drive is to say that you had an undriven spectrum, and if you are driving at frequency omega, it's trying to cause resonances between energies which are separated by omega. As soon as you have something more complicated than a periodic drive, you are allowing even more frequencies, you are allowing resonances at even more frequencies. So that will only accelerate this heating up. So driving with something, so the periodic drive was possible, the best possible hope, because you only had one frequency to, or multiples of it to allow for resonances. So for example, if you say the other extreme limit would be to have a white noise. A white noise is basically, it has support at all frequencies. That basically means that any two states can become resonant as soon as they have some finite matrix element. So that's going to be the fastest to infinite temperature. Now if you say I have a quasi-periodic drive where the frequency spectrum is some singular continuous set, even there you still have an infinite number of frequencies at which resonances can happen. So those things will only make it worse.
But like we want to see, like we have a system, we have a Hamiltonian, and we evolve it to see what is going to happen. If what is going to happen is trivial itself, then like why do we want to avoid it? Why is that undesirable? Like this is what quantum mechanics gives us, the trivial answer.
Because the question is that, okay, so the point is, because eventually once you have these, okay, you can ask the question that why am I actually dealing with driven systems as opposed to Hamiltonian systems?
Yeah.
That's because on devices you actually simulate a set of discrete dynamics. You don't actually simulate a continuous time Hamiltonian.
Okay.
That's why you want to understand. And more importantly, with Hamiltonians, you will not be able to, or rather, if you have a driven system, there is a possibility, even just from a theoretical perspective or an academic perspective, you have the possibility of realizing new phases of, or new responses of matter which are not possible in Hamiltonian time-independent Hamiltonian systems. For example, you cannot have a time crystal in a, I'm not saying that the time crystal is the most interesting phase of matter one can think of, but it's one phase of matter which appears only in driven systems and not in Hamiltonian systems. So it's basically exploring a larger possibility space of phases.
Thank you. Thank you.
Something is entangled. Okay, thank you. I get the impression that what you're using is some variant of the Zeno paradox, some adaptation of the Zeno effect, quantum Zeno effect, to get this. The first question is, at the beginning, you said kinetic energy can become very large because of the beta becoming...
Beta can go to 0, yes.
Yeah. Which will be, so the issue is, presumably at that level, relativistic effects become important. Okay? Then let me ask, I am not very clear. So in that case, I know by general theorems that the Hilbert space cannot be factorized. It cannot also be factorized for identical particles. If you have identical particles, these partial traces will give wrong answers.
Yes.
So it is not very clear to me. If it is if it is an infinite system, also what is meant by the tensor product comes into issue. Okay? What is the topology for the complete? And they do make a difference. So it is not very clear to me what your system is.
Okay. So yeah, that is because I did not specify my system. So let me answer one by one. So relativistic effects don't enter for us because we always deal with bounded spectra. Okay. So we always have a bottom of a spectrum and we have the top of a spectrum.
Yeah.
So what infinite temperature means for us is that the state populates the entire spectrum in a democratic fashion. So there is no sort of notion of relativistic dynamics entering.
So let me say, there is a theorem, there is something called the Fermi effect, you may know it, Fermi paradox. Okay? So that essentially shows that one cannot factorize the Hilbert space into factors. The observables can be localized, but not in the sense, in the causal sense. So let me ask another question. What is the effect of causality here?
So the effect of causality here, okay. So let me answer your previous question about Hilbert space or factorizing the Hilbert space, and then I'll answer the question about the causality. So in our system, we are not trying to factorize the Hilbert space of particles. Okay, so we are working with lattice systems.
But you are partially tracing.
I am partially tracing, but
That
what I am
is-
partially tracing are sites of a lattice.
That is a factorization in the Hilbert space.
That is a factorization of the Hilbert space, but that is something I'm always allowed to do because I'm not in continuum. I'm on a lattice.
It doesn't matter. If it's identical particles, you can't do this.
No, I mean, okay. So if I have a lattice, let's say, and I have, on each lattice site I have some quantum, let's say, spin halves sitting. So I can always take any state. I can take any state, and you give me any basis, okay, or any local tensor product basis, because I can obviously construct a tensor product basis of some sigma z on site I cross sigma z on site I plus 1 cross so on. This is a valid basis, and I can write my state as this entire vector sigma times sigma. So this is my some sigma vector summed over all the sigma vectors. So this is a valid state, and I can always do a Schmidt decomposition of this to get sigma A, sigma B. Okay. So I'm not trying to factorize between identical. I'm just saying that I have a lattice. I have sites on a lattice, discrete lattice, and I am cutting between two parts of the lattice. I understand I cannot do this in continuum.
Let me say I don't agree with this, but we will talk later.
Sure, yeah. And the question about causality, I think the fact that the entanglement grows linearly and actually has, we can talk about this later, but we define something called an out of time ordered correlator. So that actually that gives me a light cone in how quickly the entanglement spreads between two parts of a system. That basically is what carries the notion. Not quantum. I mean, I'm not talking about fields at all. I'm just talking about, let's say, spin operators.
Then I have to.
Okay, well, we can then talk about it. But there is no problem in sort of doing a Schmidt decomposition on a local tensor product Hilbert space where the local Hilbert space dimension is finite.
So that will be the last.
So when you have this eigenstate thermalization hypothesis, so do you take so where is the information gone that the system is strongly interacting or weakly interacting? Is it true for any generic Hamiltonian, or is it only true?
It's true for generic non-integrable systems.
Non-integrable system, but it doesn't depend on the strength of the interactions inside. And how do?
I mean, of course.
Is there a proof of it, or is
so there are quasi-proofs of this.
Okay.
So of course, that's why the name is still eigenstate thermalization. There are very definitive tests of this.
Because I would assume that if you have like a very strongly correlated system, then the entanglement spread will be much faster than in.
No, it's always no. There is a proof called there's a proof of the entangled. Okay, so if you have short-range interactions, then there is a proof that there is a finite velocity of any information spreading. It's called the Lieb-Robinson bound. That is a proof. And one of the reasons why at least condensed matter people got interested in the OTOC was because this OTOC actually saturates the Lieb-Robinson bound. Most other quantities don't saturate, and in fact it's an interesting question because suppose I have some conserved quantities, they will not show any ballistic light cone, right? They'll be diffusive. Nevertheless, the OTOC even in those systems actually shows a ballistic cone.